Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to find the age of a rock when you are given the ratio of one isotope, the parent isotope, to the daughter isotope. So this is going to be very similar to the last video I made on a different problem. So let's get into this. So we're given a rock that contains a lead 206 to uranium 238 ratio of a 0.145 to 1 gram. So we're assuming that this is gram ratio. Assuming that the rock did not have any lead 206 at the time of its formation, determine its age. Okay, so here's our formula or equation that we're going to use. So let's lay out what we know and what we need to find out. So at NT, so we have this ratio, and we're going to have to do something with this. And so what this basically is saying that we have a ratio of mass of Pb206 to lead or uranium 238. So basically what this is saying is that for every 1.00 gram of uranium 238 there is in the sample, that means that you have 0.145 grams of lead 206. So we can kind of, since that's the ratio, we can use that as the actual numbers, because those numbers, the ratio is going to be the same no matter what numbers you use. So let's just say we have 1 gram of our uranium 238 left in the sample, left in this rock, and we have 0.145 grams of the lead 206. Now, the thing that we need to keep in mind is that the lead 206 came from the uranium 238. Uranium 238 decays into lead 206, and the half-life is, I'll write it here, the half-life for this process is 4.5 times 10 to the 9 years, or 4.5 billion years. So that's the half-life. So we're going to use that. So if we use this ratio as the actual numbers, then the amount that we have right now at time t, which is now, is 1 gram, because that's what we have left. So the ratio right now is lead to uranium. So according to this, we have 1 gram left. So that is the amount at time t. So we'll write 1.00 grams. Now what we need to find out is the original amount. So how do we find the original amount? Because the original amount that we had, some of it decayed. So we don't know, we don't have the original amount. All we have is 1.00 grams left. But we do know that we have 0.145 grams of the lead 206. The lead 206 came from the original amount of the uranium 238. So to get the amount that was lost, we need to convert the 0.145 grams of lead 206 back into the uranium 238. So let's do our conversions. So here we have 0. Oops, there should be a 1.145. 0.145 grams of lead 206. And so we want to convert that to uranium 238. So we need to convert that to moles. So since this is lead 206, the molar mass is 206 grams. So 206 grams of Pb206, and that's on top is going to be 1 mole of Pb206. So the grams of Pb206 cancel out. Now I have moles. And we know that for every one atom of uranium-238 that decays, it will decay into one lead-206 isotope. So that's the daughter isotope. So it's a 1-to-1. So 1 mole. So I put 1 mole of lead 206 on the bottom and 1 mole of uranium-238 on top. So moles of the lead-206 cancel out. And finally, I can use the molar mass of uranium-238 to to convert to grams. Again, uranium-238 is a specific isotope. It has a mass of 238. So therefore, 1 mole of this is going to be 238 grams. So we're going to put 1 mole of the uranium-238 on the bottom and 238 grams of uranium-238 on top. So the moles of uranium-238 cancel out. And so now all I need to do is multiply across the top, divide by the bottom, and I get my answer. And that answer is going to be, 0.1675. So 0.1675. So that's going to be equal to 0.1675. And that's going to be grams of uranium-238. So now I have the grams of the uranium-238 that came from this many grams, or I'm sorry, that produced this many grams of 0.145. So this decayed and this was produced. So now this was part of the original. Oops. Sorry about that. So since this is part of the original, then I add that to the 1.00 that I have right now, and that'll give me the original. So I have NO and naught is equal to 1.00 grams plus the amount that decayed, 0.1675 grams. So then add that together, and my original is 1.1675 grams. So now I have the amount that I have now. I have the original amount, and I have the half-life. So now I can plug everything into my equation and solve for T, which is the age of this rock. So let's go ahead and do that. So NT is 1.00 grams. So I'm going to put 1.00 grams. N naught here is the 1.1675. 1.1675 grams. And that's going to be equal to 1/2 to the power of this fraction T, which is the age of the rock, divided by the half-life. Now the half-life is 4.5 times 10 to the 9 years. So 4.5 times 10 to the 9 years. So now what I can do is start working this problem out. So let's take the division of this. So if I divide those two numbers, 1 divided by 1.1675, I get 0.8565. So 8565? 8565, not 86. 8565, and the grams cancel out, so this is unitless. So I have now that's equal to 1/2 raised to the power of t over 4.5 times 10 to the 9 years. So now I can take the log of both sides, because what I want to do is I want to get this power here down in front. I want to get this not as a power, but as a normal fraction. So in order to do that, I need to take the log of both sides. I'm going to take the log of this, and I'm going to take the log of that. So let me do that. Let me do this in a separate step since you don't have any room. So I'm going to take the log of 0.8565, and that's going to be equal to the log of 1/2 of t over 4.5 times 10 to the 9 years. So now that I have this in log, I can take this power here and put it in front of the log. The law of logs allows me to do that. So then what I have is the log of 0.8565 is now equal to, I'm going to bring this down in front, so it's going to be t over 4.5 times 10 to the 9 years, and this is going to be multiplied by the log of 1/2. The log of 1/2. So now I can divide both sides by the log of 1/2. Log of 1/2. The log of 1/2 over here cancels out. And now I can find that. So let's calculate that value. So I'm going to take the log of that number and I'm going to divide it by the log of 1/2. And there I get 0.2234. So I get 0.2234 is now equal to t over 4.5 times 10 to the 9 years. So now all I need to do is multiply both sides by 4.5 times 10 to the 9 years, and I get t is equal to 0.2234 times 4.5 times 10 to the 9 years. And when I calculate that out, I get 4.5. I get 1.01. So 1.01 times 10 to the 9 years. So that, ladies and gentlemen, is the age of the rock. It's just a little over 1 billion years old. And so that is how you solve this sort of problem. I hope you enjoyed this video. If you enjoyed the video, if you liked it, if you learned anything from it, then please like the video, share it with your friends. Make sure you hit that like button. Also, make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all. And finally, put a comment down below on the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.